We're going to be talking about Jim Al-Khalili. This fellow is into, once a mathematical physicist finishes with physics, he's got nothing else to do because there's nothing new to invent in physics. There's nothing in quantum, there's nothing in relativity, and string theory is nonsense, and it's just math. They can't even figure out how they're ever going to be able to run an experiment, which they claim is part of the scientific method, to prove or in any way test the string theory, the existence of string, the vibrating strings, whatever they do over there, and so there's nothing more for all these people to do after they finish with quantum and relativity. And at that point, what do? Well, what they do, they start branching out. Some go into psychology, psychiatry, and consciousness, all that nonsense there. And others go into, like Al-Khalili, into biology. They want to especially introduce quantum into biology. They call it quantum biology. And that's what I'd like to talk to you about today. Okay, so what is Al-Khalili's argument in general terms? Okay, this is the bottom line with Al-Khalili and what he thinks, right? He says, heretofore incomprehensible biological processes today have explanations thanks to the fact that we, quantum mathematical physicists, stepped in to solve these long-standing mysteries for the biologists. That's essentially his argument. He's saying, look, you guys couldn't do your jobs. We've mathematical physicists, they call themselves physicists, we had to step in to help you guys because you wouldn't be able to solve all this stuff because it all works at the quantum level. And so that's going to be his argument. And like I said last time, he starts out with a sales pitch in which he says that, quantum is proven. The theory of quantum is proven by technology. That's in the background, okay? Okay, let me put this here. And so he starts out with this bird known as the European robin, okay? It says it migrates constantly from merry old England all the way to Spain in the winter, I guess, and then comes back in the summer back to England. So it goes back and forth. And so he thinks this bird has something to do with entanglement. It's an entangled bird. And quantum entanglement, right? And why? Well, he says that it's going to use entanglement essentially to get its bearings. It's going to use the magnetic field of the Earth, which it can detect, okay? And so that's where he's going to go with this bird. He's going to show that this bird, part of biology, the study of biology, has lots to do with quantum mechanics, especially with all these new, or you could say new, I think in the last 50 years they came up with most of these irrational explanations for how the quantum universe works. Okay, and so he starts out by saying the following. He says, for decades now, the robin navigates was one of how the robin navigates was one of the greatest mysteries in biology. And of course, that is until quantum came to the rescue, right? The most recent discovery has caused a sensation. It navigates using one of the strangest tricks in the whole of science. Guess what? It utilizes one of the quirks of quantum mechanics. Quirks, I would call it irrationality, right? I mean, let's use the right words. This is a world in which objects can spread out like waves. Quantum particles can be in many places at once and send each other mysterious communications. Now, how does that sound? Does that sound scientific to you? Just, first time you hear something like that? Okay. This is the only explanation that could bring all these results together. In other words, quantum, right? The robin has a biological compass somewhere in his brain. Apparently, according to Al-Khalili, says it has to do with it entering through his eyes, just like photons enter our eyes, right? It navigates using the Earth's magnetic field. Okay, so we got that rolling. Let me get this guy out of here. And so here's the entangled robin. Okay, according to Al-Khalili, says the puzzle depends on one of the truly mind-boggling ideas in physics, but don't worry if you find it hard to understand. He's already, warning you. You're not going to understand any of this. The way this happens defies all common sense. No kidding. So they're going to try to explain to you something that defies all common sense. That's his starting point. Now, go get your popcorn, your beer, because it's going to be lengthy. The idea is called quantum entanglement. It involves particles that seem to communicate faster than the speed of light. I thought Einstein proved, right, with special relativity, that nothing could travel faster than light. Here we are 100 years later, and these people still cannot accept that. On the one hand, they glorified Einstein, said, look, he proved, he demonstrated, he showed us that nothing can travel faster than light. And now the first thing they say, oh yeah, in quantum, that happens all the time. So which is true? I mean, does this debunk special relativity? How can they say this and at the same time glorify Einstein and say Einstein was right when here, they're saying the opposite? If Einstein was wrong, just say, hey, Einstein was wrong. Sorry. He was a dummy. He didn't know what he was talking about. No, they glorify Einstein on one hand for inventing the nonsense of relativity, and then they also want their cake and to eat it too. They also glorify quantum, saying, oh yeah, by the way, we do in quantum travel faster than light. Maybe gives hope to people who want to travel, to space, to the nearest stars, to colonize the galaxy. Maybe that's why they do it. I don't know. The idea is called quantum entanglement, okay? And extremely delicate experiments, very delicate, okay, have shown that subatomic particles really are entangled. In other words, they're connected, but we don't see the connections, okay? It means that they can subtly and instantaneously influence each other across space. In fact, we had Brian Greene saying that it doesn't matter if it's on the other side of the universe, that particle is entangled with the one here. Well, it sounds like they're connected somehow, right? Maybe we just don't see the connector. The same thing is going on inside the robin's eye. When a photon enters the robin's eye, obviously he's thinking a photon is a little particle, right? It creates what is called an entangled pair of electrons. So the photon enters and two electrons become entangled. Now, whether they were entangled before the photon came in, that's an interesting question we have to ask. But they always say that it's only when you look, when you try to measure that, you get these weird things, right? Like in quantum mechanics, the electrons are mysteriously linked. I guess he's describing the rope. Is he trying to steal my rope away from me? This is the ultimate secret of the quantum Robin's compass. Okay, so what's the deal? They're inextricably linked. Okay, and a lot of this just sounds to me like spooky action at a distance, as Einstein mentioned or categorized it, as described it. Einstein didn't believe in quantum mechanics. To me, it sounds a lot like the Bible. It sounds like this, okay? You read these passages in the Bible, here you have entanglement, okay? Am I a God at hand, said the Lord, and not a God afar off? For though I be absent in the flesh, in the body, yet am I with you in the spirit. So he's with us in the spirit, okay? A particle is not in the flesh with the other particle. They're just in the spirit. Word spirit, brings me bad memories of, dark ages. For with God nothing shall be impossible, and neither is it with quantum mechanics. Not only impossible, but there's no such thing as irrationality. Everything that they can think of is, even if they cannot imagine it, they say, yeah, it's okay. It passes the test. It passes quantum, and they just invent principles and laws to back what they're interpreting, the physical interpretation they give you. So since the physical interpretation makes no sense, it's idiocy, they have to create principles like complementarity and uncertainty and all these other nonsense they have, their entanglement and so on. Okay, here is entanglement. Okay, here's a simulation of what they're talking about. The guy sprays paint the statue, and the exact picture on the screen or on the wall there gets the same painting on the head. Action at a distance. Now, does that sound like science to you? Right off the bat. This is what these people are proposing. So is quantum a rational physical interpretation? Well, it doesn't seem like it, because here these people are telling you nonsense. They're saying there's this action at a distance without a mediator. It's instantaneous, and when you do something here to this particle, the other one immediately reacts to it. And if the other one over there reacts, that means the one on the other side of the universe reacts, and all particles in the universe react with respect to this one. It's not just one particle that reacts, because that's the one you measure. How about the others? The gazillions and gazillions and gazillions, or like Carl Sagan would say, billions and billions, right? What happens to all those particles? Are they also entangled to this one particle that you're touching? So you move all the entire universe with this particle? It does sound a lot like the rope, connected to everything. Then you can make sense of it. But without the connection, you're putting spirits. Then you're putting what God just said. He's with you spiritually, not in the flesh. Okay. Al-Khalili continues. He goes with the nose now. He says, why do you smell? What? I mean, why do you, smell with your nose? Not why do you smell, okay? For decades, biologists thought they knew how our noses sniffed different chemicals. But mathematical physicists believe there could be a new ingredient in the mix, and it smells like quantum mechanics. Ooh, I don't know. How does quantum mechanics smell? The standard explanation is that it has to do with the shape of the molecules, okay? The scent molecule has a particular shape that allows it to fit into the receptor molecules in our nose, okay? Triggering that unique smell sensation. In other words, what Al-Khalili says is that molecules from the outside, from the gas or whatever odors coming to your nose, lock in. It's like a lock and key mechanism where one molecule locks into your nose molecule, and if it fits, well, it gives you a certain trigger into the brain and says, oh, I see what I'm smelling. I'm smelling, perfume or whatever you're smelling. Okay? Garbage. The standard explanation is that it has to do with the shape of the molecules. Again, it's lock and key. Okay? The scent molecule has a particular shape that allows it to fit into the receptor molecules in our nose, triggering the unique smell sensation. So he asked now, so why would two molecules with different shapes smell the same? Okay, because there are odors out there that are the same as other odors, but they have different molecules. So he's trying to explain that. He says, oh, we can do it with quantum. Okay, so how does he explain it with quantum? Well, he does a little dance here. He says, quantum biology has a head-splitting explanation. I'm sure it has. It's got to be head-splitting. It says our noses aren't smelling chemical molecules. They're listening to them. Yeah, you heard right. It's not just the shape of a scent molecule that matters. The quantum theory of smell is all about vibrating bonds. Bonds? Yeah, they're talking about, covalent bonds and chemical bonds, in general. It's like a particle of sound. Okay, they have the phonon. Listening with our noses. That's what he says that smell is, according to quantum biology, quantum whatever. Okay, the new or the latest, I guess you could say, quantum explanations, decoherence, entanglement, superposition, tunneling, those kinds of things. That, he's referring to all this magical stuff they cannot explain, but they introduce as if they knew what they were talking about. Those are the physical interpretations. So you say in this case it's a vibrating bond. Okay, what's happening? What he's going to lead you into is that the particle turns into a wave, and the wave can do anything it wants. It's all over the place. So whenever they need to cover the whole room, they use the wave. They can't use the particle because the particle is concentrated at a point. But, you know, when they have to travel something, you know, and say, well, this thing moves from here to there, that's when they bring the particle. Okay, even though there's a so-called physicist, mathematical physicist, who said it in reverse. He says, light travels as a wave and arrives and departs as a particle. These guys are saying more or less the opposite. He says, you know, the particle comes from the sun or from wherever, and when it reaches the biological molecules that it's going to hit, it disperses into waves. It just turns into waves, and because it has to cover the whole cell, the whole molecule. It has to act simultaneously everywhere. And since they cannot explain it, they have to bring these notions from quantum mechanics. Okay, that's where they're headed with all this. Okay, so what does he say? This is what he's referring to. He's saying, look, these are the vibrating bonds. Okay, and the question is, what are those bedsprings? I mean, I don't see them in the standard model. So what are they referring to when they say bonds? You know, what are they talking about? And of course, they'll never answer that because they don't have a physical entity to put into that word bond. When they talk about bonds, they're talking about abstract descriptions, mathematical descriptions. They're talking about force. They're talking about energy. They're talking about charge. They're talking about a lot of nonsense, but they're not putting a physical object in there for you to see. And they put a bed spring, and you say, is that what the bond looks like, a bed spring? No, that's just a simulation. You're not supposed to take it literally. Then what is there? What's holding two atoms together to form a molecule? And that's when they run into trouble, because that's when they start talking about orbitals and whatever those orbitals are, because what is an orbital? It's just a region where you can find the electron bead. So it's like you never get a straight answer. You never get an object. You never are able to visualize a physical object in there, and they'll never put one in there because they don't deal with objects. They're all mathematicians. That's why you won't see it. Okay, so what is a phonon? Okay, here it says, okay, phonon. Phonon, collective excitation in a periodic elastic arrangement of atoms or molecules in condensed matter, specifically in solids and some liquids, okay? Often designated as a quasi-particle, it is an excited state. Whatever an excited state is, I don't know, New York, California, those are excited states. In the quantum mechanical quantization of the modes of vibrations for elastic structures of interacting particles. Phonons can be thought of as quantized sound waves. Now we have sound waves, and they're quantized. They're going to turn the wave into a particle, okay? Similar to photons as quantized light waves, okay? So now they take this longitudinal wave, they're going to turn it into a particle like I showed right there at the bottom, okay? Quasi-particles, emergent, what are they? Those are emergent phenomena that occur when a solid behaves as if it contained different weakly interacting particles. So what are quasi-particles? They're phenomena. What are phonons? They're excitations. All these are verbs. What have they done? They've turned them into particles. They've turned the vibration, the excitation, the waves, they turned them into particles. And yeah, when you can do that, then you end up with something like this. Here I've tried to illustrate that, okay? You've got all these particles that are vibrations of longitudinal vibrations of sound, but they're like drops of sound or particles of sound that travel through the air. So it's not only vibrating locally, turning into a particle, which is what they're dealing with here, but these things are traveling. So you know, it's the wave-particle duality. Particle, always, whenever they can't answer a question, they turn it into a wave. Whenever they can't answer the wave, they turn it into a particle. And you keep chasing your tail around trying to figure out what these people are talking about at any point in time. And yes, you will not be able to figure it out. Aside from the fact that there is no such thing as a wave. You have to identify what it is that is waving, and they never do that. They just say the particle turns into a wave. What does that mean? It turned into a concept, it turned into a verb. What is a wave? Wave is just a verb. It's what something does. You know, the ocean waves, the water is the matter, is the thing, the object. What it does is wave. There is no physical object called wave, not in physics. In ordinary speech, yeah, but not in physics. And so this is the problem, that they're using words that they are treating as physical objects, and wave is one of them. Okay, he doesn't stop there. He continues, and now he's going to talk about another phenomena of quantum, which he wants to introduce into biology, and he uses the tadpole turning into a frog as an example. You know, the transformation from a tadpole to a frog has never been fully explained, but the big mystery is how it happened so fast. Well, the queen there, the girl, she was able to kiss the frog and turn him into a prince instantaneously. So I guess they just need a quantum kiss or something. I don't know. What is this guy talking about? How something morphs from A to Z in a split second? Well, let's see what he has to say. A tadpole is held together by long ropes of proteins knotted together by chemical bonds. Again, chemical bonds. And it looks like he's talking about the ropes, right? Because he's always introducing an elongated object to do his explanation, but he never identifies that. He just talks about all these concepts such as bonds and waves. He never really comes in there and said, this is the physical object that's in that invisible world, which is what he should be doing. Okay? He doesn't do that. Enzymes are the little machines inside the cell that do the chemical transformations, okay? The enzymes inside the tadpole snip the collagen into small pieces. That's their job, okay? But how do the enzymes break down the molecules apart so incredibly fast? They're gonna chop the bonds, whatever the bonds are. We still don't know what the bonds are, but they're gonna chop the molecules into pieces, meaning they're gonna break those bonds, right? To do this, enzymes have to move protons about, okay? So we're gonna be moving protons, not atoms. They're gonna be moving protons, okay? But this takes a lot of effort, meaning energy, right? And time. Too slow to justify the metamorphosis, okay? Okay, so he's gonna break the molecule apart. Let's see what he does with that. He goes in there and he says, look, this is a definition of a chemical bond, by the way. We had to look it up to find out if there's any, maybe there's something I don't understand, about what the word bond means. Chemical bond is a lasting attraction. Attraction is a verb. So if that's what a chemical bond is, all they're talking about is a verb. Between atoms, ions, or molecules that enables the formulation of chemical compounds. Again, attraction is a verb. So if a chemical bond is a verb, it's not a physical object. It cannot be used as a physical object, and you can't say you're going to break what is not a physical object. So I don't know what Al-Khalili is going to break. If he's going to break a verb, he's going to break a run or a fly or a swim. What's he going to break? A jump? The bond may result from the electrostatic force of attraction. So what is a bond? A force of attraction? We still don't understand. We have verbs. All we have is force, which is a verb, and attraction, which is a verb. Between oppositely charged ions, as in ionic bonds, or through the sharing of electrons, as in covalent bonds. Well, if you share something, you still haven't told me what the bond is. What do you mean share? What are you sharing? Are you sharing a rope? If we're sharing a rope like this, then we can understand it, but he's got to identify that object. What is it that they're sharing? Are they sharing love, information? What are they sharing? So it's all concepts. At no point does he introduce an object in his entire dissertation, okay? And yeah, he continues with concepts. He continues with it. He says, look, enter quantum tunneling. Obviously, he's got to introduce that. There's an energy barrier. The proton needs to get to the other side. In other words, to do its breaking up and so on, right? Rather than jump over the wall, the proton tunnels through as a phantom through a brick wall. Yeah, I mean, what are we talking about? Religion here? We're talking about phantoms, angels, spirits, or are we talking about a physical object? Are we talking physics or religion here? Without quantum ghosts, his words, not mine, ghosts, phantoms, spirits, angels. That's what he's talking about, okay? Without quantum ghosts, the metamorphosis of a tadpole into a frog would be impossible. Yeah. Sounds like he's talking religion. I thought he was going to talk about physics, something about physics, but it turns out he's bringing ghosts, phantoms, spirits into the dissertation. Okay, and so this is how he does it. He has this cannon, atomic cannon or whatever, the enzyme, and it's going to shoot the proton cannonball right through the wall without making a dent in the brick. That's what he's going to be doing. Okay, so he's not going to shoot over the wall. He's going to take the shortcut. Like the relativists take a shortcut to get to another star. They instead of going at the speed of light, they just take a wormhole and cut across all that distance by taking the shortcut, right? These guys are doing the same thing. He said, don't jump over the wall. That takes too much time, too much energy. Just go through it. And I said, well, I can't go through it. Oh, yes, you can. See, and they just do it. Magic. Take magic wand and say, we did it. Now, does that sound like science to you? Or this sounds like religion to me. I don't know. Traditional religion, okay? Okay, so here's a proton. This is what it looks like, more or less. You got the 3 quarks there. We don't know why they don't fly apart. We don't know what that big ball that's holding the 3 balls in there is. What is that ball? Can you make a ball, a sphere, with 3 little balls? Here's your challenge. Bill Gates' challenge to you. Take any 3 balls, tennis ball, golf balls, footballs, whatever balls you want, right? And see if you can make a ball with them. I was able to make a triangle more or less, but not a sphere. And these guys have this sphere there, which is supposed to be the proton. It's got to be spherical. And what's holding them together? Well, it's this gluon, this strong force. And as you can see, they don't put how it's held together, but we know how it's held together. We saw that in a couple videos ago where we have the Bedsprings, okay? So that's how they're held together. Okay, so that's the proton, okay? And now you're going to take this bowling ball compared to the electron, right? 1,800 times more massive, okay? He's going to take this proton, he's going to shoot it, okay? And they're going to shoot it along the accelerator, okay? Well, how do they know they're handling a proton? I mean, they've never seen an atom. Here they're saying they're stripping an electron from the atom, they're leaving a proton, and they're going to accelerate a proton. This is what they're saying that they're doing. This is their physical interpretation. Well, I can just as well say that what they're accelerating is actually, an angel maybe. Here's the angel. Maybe that's what they're accelerating. I mean, I don't know. You tell me. How do they know they have a proton in there? And here's one way that they would show us that they're actually accelerating a proton, and that's by starting to identify, the atom. If they can tell me what their atom looks like and how that electron bead remains faithful to the proton to begin with, before you do anything with the atom, right? Then we can conceptualize what they're talking about. Right now we have a problem with the atom, with the quantum atom, because we don't know what that golden or yellowish center is that is between the proton and the electron. We don't know what that is. Please identify, what is that? Well, Rutherford says it's empty space. Al-Khalili said the other day that based on, the people who educated him, that stuff is made of particles. So we have electron is bound to the proton by particles. Okay, let's concede particles. How did they do it? How do all these gazillions of particles between the proton and electron, which they say is empty space, the empty space in it, how did they do it? Tell me the mechanism. Are we talking about sand? Are we talking about a gas? What are we talking about? What is that yellow stuff there, in between the red proton and the purple electron? We need to identify that stuff. Otherwise, we can't explain or justify why the electron remains faithful to the proton to begin with. And so, yeah, again, these people are saying they stripped the electron, they accelerated the proton. They could be just as well saying, hey, we accelerated an angel. No difference. Okay, he does another magic trick, his fourth one. He says, look, here we have life in the form of plants, and they receive all this photosynthesis. They manufacture, they have this process in which they manufacture all this biomass on Earth. Okay, he says at this very moment there is a bullet passing on the other side of Venus, coming towards the Earth, and has this tree's name on it. That bullet's going to hit the tree, right? That bullet is a photon, nearing the end of its long journey from the sun. Okay, you see the picture there? Okay, that's essentially what he's talking about. He's saying light consists of photons, and if we look at just any single photon, he's talking about a little particle, maybe a packet of a wave packet like we just saw with a phonon. Okay, so we have this packet of energy, this packet of waves or whatever it is, and it's going to come and hit the tree. Where does he get this? Well, he got it from his ancestors, people who told him that this is what they proven, and so he just believed it because he went to college and he says, oh, okay, that's what I memorized, and this is what I was taught to repeat by rote. Okay, so that's what he's doing. Okay, but let's concede. So we have this little particle. Okay, let's find out what he does with it. He's got this little, because he's going to explain something in biology with this nonsense. Okay, so let's find out what he does with it. He goes in there and let's see, I lost what I was going to put in there. Give me a second here. I think it's this one. Oh, yeah. Okay, so he's going to take this photon. He says it's going to do something. When the photon hits the cell, okay, a cell, biological cell, right? It knocks an electron out of the middle of the chlorophyll molecule. This creates a tiny packet of energy, whatever that is. Okay, Richard Feynman, Nobel Prize, he said, we don't know what energy is, but he's talking about a packet of what they don't know what it is, called energy. Okay, fine. Called an exciton, which he calls exciton. He calls it exciton, I think, so that people don't know where the word comes from. No, it comes from exciting, from excitement, from excite, the verb excite. And that's why it should be really pronounced exciton. I like that better. It also rhymes with phonon and photon, exciton, right? They're all, I think that's the way it should be pronounced. The exciton bounces its way through a forest of chlorophyll molecules, okay, until it reaches the reaction center. That's where its energy, whatever that is used to drive chemical processes that create the biomolecules of life. Great. We still don't understand anything because we don't know what physical objects we're dealing with here. We've got all these concepts, okay? The exciton wave, I thought it came in as a particle, the photon, and hit. All we had was particles. Suddenly that turns into, it talks about a packet of energy, okay? Packet, you would think it's, compressed, a little bundle, something, Now he says, now it's a wave. It's a spread out wave. He suddenly turned it, magically, without you noticing, turned it into a wave. He had that up his sleeve. The exciton wave is not going this way or that way. It is following all paths at the same time. See, you see why he had to convert it into a wave? Okay, because he needs for it to cover all the bases. Here you have one player, right? The guy hits, and he doesn't go to first base. He doesn't go to second base. He doesn't go to third base. He's at all three. He covered all the bases. Okay, so that's how it works in quantum. Man is at three bases at the same time. Same guy, okay, same great player. I'd love to have him on my team. Okay, so what is an exciton? We have to look it up because all I've got so far is that some kind of energy thingy. Okay, so you look it up, and well, I think I found it in a standard model. I think you'll find it in there somewhere. Okay, an exciton is a bound state. Again, what is a state? Of an electron and an electron hole, which are attracted to each other. Again, attraction. That's what it is. By the electrostatic Coulomb force. Force is a verb. So here they have this word force, which is a verb, okay, and they talk about attraction. Again, we have this verb of a verb, force of attraction. So far, all we have is verbs. We still don't have a noun. We don't know what physical objects is mediating this whole transaction. And in physics, we can't use verbs of ordinary speech or nouns of ordinary speech and introduce them as nouns in physics. No, in physics we have to be very discriminatory. We go in there and we analyze what the guy is introducing. So if you introduce the word orbital, that might be a noun in ordinary speech. For the purposes of physics, orbital is a verb. The word motion is a noun in ordinary speech. When you introduce it into physics, it becomes a verb. So all these are verbs. Force is a verb, and so this exciton, which is an attraction or a force of attraction, is all it is a verb. So far we got verbs. So we're moving verbs around. Okay, it is a quasi-particle. What was a quasi-particle? A maybe particle. One that is not quite a concept or an object. It's somewhere in between. It's in this limbo, in this no man's land. Okay, the quasi-particle that exists in insulators, semiconductors, and some liquids. The exciton can transport energy, verb, without transporting charge, more verbs. So far we have is, what is a charge? It's a charge is any of different quantities. In the case of what he's talking about, electrical charge, it's 1.6 times 10 to the minus 19 coulombs. So that's a verb. That's just a number. Number is the verb to count. That's all it is. That's the meaning of the word verb, the word number. Number is a verb for the purposes of physics, of science, right? And so he's moving 1.6 times 10 to the minus 19 coulombs, which is a relation. That's it. That's what he's moving. So far, we understood absolutely nothing about this excited exciton, okay? And here's decoherence. This is how they typically illustrate it. Okay, in quantum physics, an atom can be excited and not excited at the same time. So we have excited and not excited, and they can be at two locations or positions, as they call it, at two places at once. And they can be at many places at once. Okay, so if you're going to introduce magic, you can do anything you want. I mean, is this an explanation, a scientific explanation? Are we listening to a scientist or a preacher, a preacher of the Dark Ages, a monk? I mean, this guy is just introducing, for all his processes so far, he's just introduced magic. And it's irrationality because, I can do magic too. I can say, look, I created this rabbit from the hat. And someone asked me, what's a trick, Bill? How did you do that magic trick? No, it's no trick. I actually did create the rabbit from empty space. Length, width, and height, bloop, here you have the rabbit. That's what these people are doing. And they call that science. And they say it's been proven. No, they haven't even proven it. What they've done is they said, look, we saw something in the lab. This is what we saw. And when they bring it in, they interpret it according to the particle hypothesis. And of course, you cannot explain the subatomic world with particles. That's the problem. And so when you try to explain it with particles, you have to introduce magic. You have to do, spirits. You have to do excitons. You have to talk about positive and negative. You got to talk about a lot of energy, wave packets. You got to talk about a lot of nonsense because because you can't explain it with particles. That's the problem. And so the particle can be at a given point in time, a given location, but then for the effect that you observe, it's got to cover the whole room. And how do you do that? Well, you say, well, very easy. I turn the particle into a wave, a spherical wave of sorts. And so it covers the whole room instantaneously. Wave of what? And they say it's a probability wave, wave of probability. That's it. You won't get any farther than that. And if you didn't understand it, they say, well, you got to take 10 years at the university like they did, and then you'll understand it. Well, if you understood it, how come you can't explain it? How come you can't explain it to a barmaid or what, a 10-year-old kid? Okay, so let's go with a summary. And here we have it. Give me a second here. Summary. Quantum entanglement is the mechanism whereby a particle here affects another one over there without any mediating agent. In other words, magic. Bond vibrations fail to identify the physical object that serves as mediator and does the bonding. Again, magic, because if you don't have an elongated mediator between two atoms to do your molecular stuff, your crystal lattices or whatever, then you're doing magic. You're saying this atom vibrates, the other one vibrates, they're all vibrating. Why are they vibrating? Well, because of the bond. What bond? What is this bond? James Bond? What is this bond? And they'll never identify the bond, especially like hydrogen bond, which is from a distance, like the covalent bond. They more or less, they try to get by saying, look, it's the orbitals that more or less merge, which is again what the rope model proposes with real objects. But they say it's the orbitals, they kind of overlap. Okay, how do you do hydrogen bonding, which is just a little line that connects two like the oxygen to the hydrogen, right? How do you do that? Well, then they have no no answer for that. They don't have they can't put what are they going to put, a line? They can't put anything for a bond, for the word bond, a physical object. They just talk about bond and energy and charge and field, but they will not put a physical object there. They'll do it, with a line, like in the stick and ball model. But when you ask them, well, is it a stick? Is it a little line? What is that line? That's where they fall back and say, oh, you got to go 10 years to the university to understand what that line is. That's the answer you're going to get. Okay, a phonon is an abstract concept that the mathematicians morphed into an object because they have no clue what invisible entity is doing what they are observing. See, they can't explain this with particles. That's the issue. A quasi-particle is a verb that the mathematicians converted into a noun. Okay, again, it's all these verbs, these concepts. A quasi-particle is a verb, right? Tunneling is a physical interpretation in which a quantum cannonball goes through the walls without causing a dent in the brick or mortar. So, yeah, I mean, if you can shoot a cannonball through the castle wall without even touching the wall, maybe it doesn't even kill the soldiers on the other side either, because what is this? Is this an abstraction that you're shooting? What are you shooting? Explain the process, the mechanism by which the proton avoids breaking the bricks of the castle. That's what you need to explain. If you can't explain that, you don't have a theory. All you did is magic. And then the quantum decoherence, which is the last part, means that a stone thrown in the lake morphs into the water waves that disperse from ground zero. So you threw a stone, you threw a nickel in there, right? Or it fell. And you see all these waves. And you say, oh, I'm going to look for my nickel. No, don't look for it. It went with the waves. The waves, the nickel turned into those waves that spread out. You lost it. You lost your nickel. Okay, so Al-Khalili explains all this, and so the question is, where does he get all this? And did he just memorize in school? That's it, to get his degree, to get a good job and a career? That's it. That's all he does. He never thought. He never used his brain for anything. He just memorized, studied for the test, and passed. That's it. That's how he got through mathematical physics. That's how he got his degree. And he will say that he stands on the shoulders of giants, okay? That you had all these giants in the past, Einstein, Newton, maybe Rutherford. And so here we have atom man Al-Khalili. We saw him a couple of weeks ago, yeah, and he's standing on the shoulders of two giants there. Niels Bohr and Feynman, both Nobel Prize winners. You know, these people believed in quantum. They passed it on to him or to his teachers and then to him, whatever. So this is where he got it. He got these ideas from these two fellows, essentially, and others, right, like them. And the question is whether these guys are giants or he thinks they're giants in his little mind. He thinks they're giants. Maybe when we look deeper, you know, these guys are just uh, mental midgets. That's all they are. That's all they were. And maybe ants are bigger than them. That's my conclusion on good old Al-Khalili. Okay, so I don't think he's. What can you say about a guy like that? This guy who just memorized because he never even questioned whether what they were teaching him has any validity whatsoever. Maybe he said, "Well, that's so strange. That's so weird." Well, if it's weird, where's your skepticism? Where is your where are your rejoinders? Where, did you question your teachers and say, "Hey, you know, this sounds irrational to me"? And they convinced him that it's okay to be irrational in quantum. Is that it? And they kept going. Is this how his teacher memorized? And is this how his teacher got memorized decades after decades? So all we're passing around is all this nonsense and nobody questions it, whether any of this has any validity. Has to make you stop and think. We're in a very strange world today. Okay.